Hello, hello, hello. Welcome back, welcome back. Um, so first thing to say is congratulations to all of you and all of us. Pat yourself on the back because we are at the very last lecture of this semester. Um, so this is the end. Um, so I just want you guys to have a little bit of fun about this. So this lecture we will try to cover chapter 7, and this is when you actually get to the fun part of this whole digital design, digital system design, because now we're getting back to something we are more familiar. So we're going to work with the concept of memories in this chapter. We also just figure out what is RAM and ROM. Of course, you guys mostly are computer engineer and electrical engineer, so a lot of computer nerds in here in this class. So I hope that you enjoy this chapter, just for the sake of learning. Don't worry about test or exam or something. Uh, as I promised, one of the extra credit question will be for chapter 7, just to make sure that you keep learning to the end. It will be one of the example either in section 7.6, programmable logic array, or section 7.7, programmable array logic will be exactly the same. So, and it will be exactly the same like the example in the textbook, and the exam will be open note. So it's gonna be pretty easy. Okay, let's begin with our final lecture. So there's some overview here. Okay, so um, definition for memory. Memory is simply a place to store value. Okay, it can be stored either long term, can be stored short term also. Okay, uh, it can be comprised of a large array of devices such as flip flop to create kind of like a bank of memory. But with this definition, I want you guys to back up a little bit, okay? Because remember, you have, as you know in memory, right? Remember the graphic, the comics I gave you in the beginning. Memory is just anything that you can store information. So your brain is the term of memory, okay? So if for digital system, you try to store thing in terms of 1 and 0 because you can digitize that information into 1, 0 easily. So for computer, when they store information, usually they will try to store that in different terms, okay? In the beginning, when they design a computer, the easiest way is to store that by charge, okay? Actually, yeah, to store it by charge. So you can charge a capacitor up, okay? You can hold the voltage of the capacitor there at a certain level. Then to represent a high, level high, okay, or a 1, then you can discharge it to make it go back to 0. So that's some initial memory that you have there. There are different ways to store it. You can store memory at open circuit, short circuit. So there's different way to store memory, okay? Or in terms of, if you live through the 1890s, early 2000, or you instead of your SSD hard drive, we use magnetic hard drive, right? So those information can be stored in terms of the magnetics polarity, okay, in your hard disk. So there are different ways. So in terms of this class, for let's say the beginning, when they build a digital computer system, there are two types of memory that people think about, okay? Then now there are so many different ways to store information, but in the beginning there was two different types. The first type is called random access memory, okay? So for this type of memory, you can read from it. Okay, what's the point of memory without being able to read from it? You can also write to it. Okay, so you can read and you can also write. Okay, so now go back. Okay, now rewind your memory in here back to some of the lecture about registers. Keep in mind, registers is a place that you can, you know, it's like a placeholder for your data. Okay, so you can transfer data into the registers. You can transfer data out of the registers. Now, what is reading? Reading is when you transfer, let's say I'm trying to read my mind, my own mind. That means I try to transfer the memory in the back of my mind outside to my thought, to my speech. If I want to write a memory, I listen to the information, then I transfer it back to my mind, right? So it's the same for random access memory or RAM. If you want to build a RAM, it's very easy. You can have just a stack of registers, okay, and you can use those registers to store information. Then you can erase the information. You can write new information to it. You can transfer those information to the other one so that it's performed as a read. Another type of information is called read-only memory, okay, or ROM. So can you read a ROM? Yes. Can you write a ROM? No. Okay. And here is the difference, because so the read-only memory, usually the purpose of the ROM is so you want to be able to, let's say if you have a machine, a very dumb machine, not like really smart machine like now. If you have a really dumb machine, okay, and you want to be able to hard store, like just make an information stick to the brain, okay. You want, let's say I have a brain, my computer have a brain. I want that information to stick into the computer brain without a computer, messing around too much, okay. So this information will basically store the functionality of your computer or your circuit, your primitive circuit. So another way to say this is, in a computer system, okay, you can have ROM to store information about how the system should work, okay. Or in other words, ROM can be a program that is written into your system to tell how your system should work. Then during the functionality of your system, it needs to have some instant memory, okay. So those instant memory can be RAM, okay. So if you go deep into how memory work, and you recognize, if you just build your own computer, you recognize those RAM memory is, you cannot store information after you turn off your computer, right? So you also know that if you try to write a program into RAM, it's not gonna work well, because the information is gonna be erased every time you turn off the system. Okay, so that's a two different thing and two different function of the main two different type memory. So random access memory is able to read or write to and from RAM. Okay, and why do we call it random? It's not like it's gonna randomly pick something. Okay, the word random is because the time that it needs to access any of the memory element, any random element in your memory, is always the same. Okay, so the name random access memory comes from that. Okay, now it's important. Each value that is stored in a group is called word. It's called word. Okay, so some definition here. In a memory, you can have a unit called bit. A bit is a single memory unit that either store 0 or 1. Okay, it's a 1 base 2 value. If you have 8 bit, you have 1 byte. Okay, 8 bit equal 1 byte. And a word is a certain amount of bytes that is placed together. So let's say your computer is 64 or 32-bit system, right? So you can guess how many words your system will, like how big of the word, of each word of the system is going to be. So if you have a 16-bit word or 16-bit system, each word will contain 2 bytes. If I have a 24 word, each word, 24-bit system, each word of the system contain 3 bytes. Likewise, 32, each 32-bit words, each word will contain 4 bytes, and so on. So you can easily have a format of, have a RAM, then you have a data input because you need to put some information in it, right? Then you also need okay, let me turn off my camera here. So you also have a data output, okay, which is, let's say if your system is, I would say 16-bit system, okay, 16-bit. I just like that name because it's similar to an R name that I enjoy. So if it's a 16-bit system, the data input will have 16-bit, the data output will have 16-bit, okay, consistent like that. So inside here it contains enough space to store, let's say 2 to the k words. It will receive a command that read the memory. It can also receive a command to write into this memory, and it will have k address lines. Okay, so that means in the memory itself, okay, in the memory. So if you try to imagine, okay, so if you try to imagine, RAM is basically your, like, one RAM unit is Cincinnati, okay. Now I want to send a letter to, let's say, my friend Alex's house. I need an address, right? Because I need to know where is his house to send a letter to. So I want to write to Alex. I need an address, okay. Or if I need to read from him, I need to request some address. So every time I need to write or to read something into the memory or from the memory, I do need an address to know which memory in that RAM that I need to access or to write to. Okay, so now we are going to talk about reading and writing. Okay, so there are some procedure or some steps that you need to perform in order to read or to write into your memory. So for the purpose of transferring new word to be stored into your memory, there are these steps to be followed. So first, you have to apply the binary address of the desired word into the address line. So you need the address. Then you apply the data bit, okay, which is the input. Okay, you apply the data bit that must be stored in the memory to the input lines. Okay, then you activate write input, so you tell your write command to is yes. You activate the RAM to be able to get new information in. Okay. So in order to read from it, okay, or basically to take the information from the RAM out of it, it's also very similar. Okay, you need to have the address, apply the address into the address line, then activate read. Okay, so read and write. First step, address. Second step, depending on read or write, it would be if you write and you have to apply an input. Okay, if you read, you can skip second step. And the last step is to activate either read input or write input. So here is an illustration that you can have. So to write to a new word into RAM, so apply the address. Okay, then you can have the data. Let me turn on the laser pointer. So you apply the address, you apply the data. Okay, then you activate the write command. In order to read, similarly, you apply the address, you apply the read command, then the output will come out from here. Okay, so for the case of write, nothing will come out from here because you're not requiring any output. So there's an alternate to RAM input and output setup. Turn off this here. So you can have a memory enable input instead, a read or write line. Okay, and an address. So similar structure, just okay. Now have a single line for. Now we only have a single line for read or write and an enable. Okay. So we can actually have different mode. For example, if the memory enable is 0, it's not going to do anything, neither read or write. So if the memory enable is 1, so I can assign 0 to be write and 1 to be read. Because it's possible I can do it. What is the advantage of this in terms of complexity? There's no advantage in terms of circuit complexity. However, it can create some different advantages, such as you can basically, if you use this memory a lot, okay, and you can basically how can I say this, like basically for this scenario, you cannot mess up the system by turn both read and write on at the same time if you use a system. So that's some advantage right there. Okay, so now we're gonna go to different type of RAM. So so RAM is basically just another type of integrated circuit. Okay, and when I say different type of RAM, you can say different mode of operation or different operating mode. So there are two main types. First is static and second type is dynamic. Okay, so the static RAM is, you can make that from latches or flip-flop that can store information in binary form. Okay, the information remain valid as long as the power is applied to the unit. So remember, when you cut the power supply, all the memory is gone. Okay, kind of like a dory. So this static RAM can remember value as long as there's some supply voltage given to it. So VDD, supply voltage. It's very easy to use. It's fast also. So the read and write speed can be very quick. The other type of memory is dynamic RAM. Okay, so dynamic RAM also store information in binary form, but instead of storing the information as instead of storing information uh, like in some latches, it actually store information as in the form of electric charge in the capacitor. Okay, so you can go ahead and try to Google CMOS design, but when you design a transistor, okay, uh, you can actually so how can I say this? CMOS is stand for or MOS stand for uh, metal oxide semiconductor. Okay, so metal oxide semiconductor. So you have 3 layers there. Okay, so if you remember your electronics 1 class or your circuit class, a capacitor is basically two two metal plate with a dielectric in the middle, right? So actually, when you create a MOS transistor, you can create some capacitor effect. So you can store the information in terms of electric charge, okay, provided by the MOS transistor. Okay, so the DRAM or the dynamic RAM requires its voltage to be constantly refreshed, otherwise the value will be lost uh, by external voltage. So in order to understand this, go back to your circuit class. I don't know if you do any experiment about if you have a capacitor and basically it will constantly be discharged, right? I mean, if you you can have a capacitor constantly be discharged. So the key of dynamic RAM is if you need to keep the high level of the capacitor high, you have to constantly charge it, otherwise it just drop down. Okay, so this one is slower, okay, but it consumes less power and it's actually smaller. Okay, it's smaller in construction, so you can have a lot more memory unit inside an equal amount of space. So there's some trade-off. Okay, so you want something less power consumption, smaller, you need to do some trick with it, which is constantly charge it with a pulse. Okay, so let's go through an example of memory cells using one latch. So you have now we have an SR latch. Okay, we have input and output, enable, read, write. Okay, that's why don't we have the address line? So answer is there's only one house in the neighborhood. We don't need an address for it for now. But if you need an address line, can you think of what is the best tool to make an address line? To make an address. 3, 2, 1. So for the example in here, wait 1 second, I'm gonna go to the laser pointer quickly. Okay, for the example in here, then we have input. Okay, the input going to so we can have an input go in. Okay, output right there. So this is an example for the let's say the one single cell memory. Okay, so you can apply the read and write in here. So if you have you apply either 0 or 1 to change the mode into read and write, you have the enable pin. Okay, so if the enable is 0, it turn the whole output into 0. Also, it will turn this AND gate into 0, like nothing going on. Okay, nothing going on. But if you turn it to 1, then you enable it with the AND gate. It accepts the read and write. Okay, so if you have a 1 in here, now you enable the output to like take the signal out of this SR latch. If it's read, okay, which is 0, then you disable this. Okay, so you can use this table in earlier. Okay, so treat the whole thing as a black box. Okay, when you create your. So there's a need for decoding circuit to select memory word specific to specify by the input address. Okay, so that means if you have more than one unit cells and you have a bunch of different memory unit, you need different address for it. Okay, so now you have to figure out how to. I mean, you would code the address, you encode the address in your memory architecture, but then you need to decode the address also. So there's a concept of coincident decoding in here. So if you use only one decoder in the memory, it can be a method of sending enable signal to each word within the memory. For example, if you have a decoder like this, you can put in n bit input, and you can have 2 to the n addressable word. Okay, so this requires 2 to the n AND gate with n inputs per gate. Okay, the AND gate typically don't exceed 4 or 5 inputs. This means you must cascade AND gate to get the required amount of input. For the large memory, there's a lot of gate. So the solution is we have to split the n bit input into n divided by 2 inputs to separate the decoder. So you can have decoder 1 and you can have a decoder 2. Okay, so they can cross each other like this. So each intersection represents a location of an n bit addressable word. Okay, so a 4-bit address A3, A2, A1, A0 can be decoded with first 2-bit input, 1-bit input, sorry. Decoder 1 input 2-bit, decoder 2 2-bit input. Okay, so you can use 2 different decoder, 2 input each, and you can cross them like this. So in this way you use less hardware to implement that. So this method is called coincident coding. Another word for it is called 2D coding. Okay, so if you want, there's a figure called figure 7.7 in your textbook. Please go into it and see how they build how can I say 64-bit address system. Okay, read only memory. Sorry, not read random. So this one you can only read from it because the value is stored permanently or somewhat permanently inside the memory. So the format of a ROM, you accept a K address line as like the address containing enough space to store 2 to the K words. Okay, and the output can have an n bit wide output, and this n number is based on what is the bit number system that you want to design. There are different type of ROM, okay, and the differences in the ROM is basically depending on the different way that the path inside the ROM is made or is fabricated. So the first way is called mass programming, or you can call it like fabricated ROM. So this is made by the fabrication process, and the reason why they call it mask, because you need some mask for the photolithography process to make your memory element. So if you have, for example, if you design some program, right, so you can send your truth table to the manufacturer, and the manufacturer will try to have that truth table convert that to basically a design for your certain computer output. Okay, then the manufacturer will make the mask corresponding to whatever 0 or 1 that you want to put in your truth table. Then the mask will physically store that program information into the device by itself. This is costly. Okay, just imagine it's like tailor-made circuit. Okay, so every time you have a new circuit, a new design, you make a new mask, then you make a new device. So it costs a lot. So technically, this is not the most cost-effective way to do design, right? So fabricated ROM, not very cheap. So what are the other way? So another way which is very economical is called Programmable Read-Only Memory, or PROM. So the PROM unit contains all of the fuses intact. Okay, so it has fuses inside. So every PROM unit, they can manufacturing the same. So now they will give it to the programmer. Okay, the programmer can giving some certain 1 and 0 input into the PROM, and the fuses, when they have a high voltage, fuses, when you put a high voltage and high current through it, the fuse blow, right? Boom. So now you can actually, those fuses can be your switch, permanent switch. Okay, so when the fuses is blow, the binary state 0 can be activated, but if the fuses is intact, the binary state 1 can be given. So this is another good way to one time only program your ROM, your ROM. Okay, so that's programmable ROM. The last type of ROM is called erasable programmable ROM. So what is the difference in here? So remember, the programming of a PROM is basically, it's a hardware process. You basically blow up fuses to make your program, but the process wasn't reversible, right? It's kind of like an irreversible process. So you can understand from the word erasable here. Erasable PROM is basically the type of ROM that you can allow the program to be erased and written again. So that means you can program your ROM several times, not only once. So the way that manufacturer make this is they place the EEPROM under some special UV light, okay, for some certain amount of time. Then those radiation kind of will discharge the internal floating gates, serve as the program connection. So after everything is discharged, it's called after erasing, all of the EEPROM will go back to its initial state, and you can program it again. So I just want the last touch. Actually, there's a fourth type ROM, and if any of you work with Arduino or any microcontroller unit, you have heard about EEPROM or E2PROM. Okay, EEPROM stands for electrically erasable PROM. This device is like similar to EEPROM, but instead of using UV light, which how many of you have it? You can just basically use electrical signal. Okay, so that is more, like you can actually program it on the board. You don't have to send it back to a manufacturer to program it again and again. So if you so EEPROM is basically it's not just on Arduino. Okay, there's another type memory. It's called flash memory, and if you have a thumb drive USB stick, the type memory is called flash memory. Okay, it has an additional built-in circuitry to selectively program or erase the 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 device in circuit. Doesn't need any special programmer or any special code or structure to do it. But anyway, for Flash or EEPROM, Flash is a little bit better. You can store it for a while. The disadvantage, if you have a really old flash drive, you notice that if you use it a lot, it's getting worse. Okay, so Flash suffer through that too. Like if you read and write like that, maybe 1,000 times, 10,000 times. I don't have a number in my mind. Probably let's say 100,000 times. Okay, if you read and write it, erase it a lot, it blow. It just stopped working. Okay, it's time to move on. So it's a good type memory. You can keep it there. Maybe recycle it, but it's not gonna last forever. So if you work on your Arduino project right there, as I know, the EEPROMs in Arduino last for probably not over 1,000 cycles. So if you need an application that need to update your memories a lot, please do not abuse your EEPROM on your Arduino. So in here you can find a structure of a ROM. Okay, and I would say this is basically a fuse. This is a fuse programmable ROM. Okay, so if you see, let me turn on my pointer one more time. If you see each line here, you have horizontal lines and you have a vertical lines. Imagine these are not on the same plane. Okay, each cross section are connected by a fuse. So if you burn that fuse, now it's connected. Okay, let's go to the next slide. So if you have a truth table, that means for given certain input, I want certain output to come out. Now you can figure out how to burn these fuses. Okay, you can figure out how to burn the fuses to have a certain output that you want. For example, each line is corresponding to each address, right? So you can, so basically you have from 0 to 31 is 32 different addresses. Okay, so for example, the address 0, you have 1 for A7 and something so on. So if you have a 1, you burn it. If you have a 0, you leave it intact. So you can decode 1 and 0 by just burning the fuse or not. So hint, I think this is a pretty good exam question. Okay, I think for the extra credit question, I can basically have an 8-bit system or maybe a 16-bit system. Not 32 bits. It's gonna be too complex. Maybe I will limit the output into 4-bit or 8-bit, maybe. Maybe a 16 address or 8 or an 8 addresses system, maybe 4-bit output. Then I'll give you a truth table. I'll ask you guys to check. I'll ask you guys to cross on this map. So if you cross correctly, you have extra credit. Okay, final topic here, programmable logic array or PLA. And this is not the PLA material that you use for 3D printing, it's the programmable logic array. So the concept is very similar to ROM because you will have an array, then you use fuses, you burn the fuses, you can program 0 or 1 based on the fuses itself. So can be can implement an array of AND gate, an array of OR gate to create a circuit that produce a multitude of functions when they instructed. The circuit possess input port for on circuit in the circuit A, B, C, etc. along with each intersection in the array being able to enable or disable. So look at this. Okay, if I give you F1, F2, two functions, right? And I give you a plain POA like this. How can you program it? So in here, this is this plan, this group right here. You can call it an AND plan, which will provide you a means term or product terms. Okay. This one will sum them up. This is an OR plan, which means you sum them up. So first you have to make your means terms. So this one, what is the function of this? This one say AB naught, okay, plus AC plus A naught BC naught. So you have to make AB naught using here. So A, okay, come in, B naught, come in. So you have AB naught, okay. AC, very simple, A, sorry, and C, and A naught BC likewise, just trace along the line. You have to burn the fuses. After that, you add them up together, okay. So you go through this OR gate. So you now burn this, add them up together, okay. So finally, you ask yourself a question. Okay, then this is important question. Now you have kind of the output, right? Now you want to ask yourself, do I want to invert this function or I want to keep it the same? If you want to invert it, you will link this XOR gate to a 1. If not, you link it to 0. Okay, so this one is linked to a 0. Okay, because you burn it as 0 right here. So F1 will not be inverted, but F2. So you do the same process, you add things up together, but at the end you want to put that prime in, you want to invert. So you link 1 to this XOR gate, so you can invert F2. Piece of cake, huh? So what I can do for extra credit question is I can give you one function. Okay, I can give you one function, maybe 3 input like this, 3 input, 1 output. I'll give you the Boolean expression of the function, and I'll ask you to burn the fuses. That means just cross, put the X on it. Okay. Another thing that you should know is the fuse map of the POA. If you can describe that in the terms of an array like this with burning fuses, you can also specify that in a tabulated or a table format. So for example, the programming table consists of 3 sections, right? Product terms, input, output. So the first section here is basically just list of the term in number 1, 2, 3, 4. This section, the input, it describes the connection or the path between ABC, which is the input, and the AND gate. Okay. This section right here, the output section, it describes the path between the AND gate and the OR gate. Okay. T stands for true, which is nothing changed. C stands for complement, which is flip the whole function. So in here you can see there are 3 different values, right? 1, 0, or dash. So 1 is true, 0 is the complemented form, and dash means don't care, it's not relevant. So you can see for BC would be 1, 1. For A not BC would be 0, 1, 0. And AC would be 1, dash 1. Okay. And likewise, you can do the same thing for the output. Okay, this is the last slide that we have on this lecture. Other form of memory. So if you have POA, you can also have PAL. And let's try not to cover this. If you want, you can discover that by reading section 7.7 by yourself. But the idea is probably the same. You have an array of wire, you burn the fuses, you make the function. You can also have sequential programmable devices, which just basically implement some form of POA or PAL and a sequential circuit. So the sequential programmable device, programmable logic device, it has another form called like complex programmable logic device. It connects a bunch of PLD via a central switch matrix, and the input-output pins can be controlled by a tri-state buffer. And finally, we have FPGA, which is few programmable gate array, and you guys use this in the lab. It contains hundreds of thousands of logic blocks that are connected via programmable connection. Very wide variety of subcategory of FPGAs. There's tons of different types of them. And this is the end. So I've already tell you what the 2 questions I will put in as extra credit for chapter 7. So I hope you enjoy this class so far. Really miss being in lecture with you guys. It was fun. I will teach another class which is called Electronics 2 in the summer. So if you guys happen to take that class in the summer or sign up for the class in the summer, I will see you again in there. This is the very first time I try to move the whole lecture online, so there's a lot of difficulty and issues that may come up with, and I'm very sorry for all of the trouble that you guys may have encountered. The main purpose of the class is not to give you an A, B, C, or D or something. I just want you guys to learn something from the class. It's probably the very first hardware class that you take at UC. There's other class that I can recommend for you to take as you go into your 3rd and 4th and 5th years. One class in your curriculum is called Embedded System Design. It's a very interesting class, and is required in your curriculum. But if you understand the basic in this course very well, like how digital system work, in that class you need to learn assembly code, so it will be a lot harder. So I recommend you go back and try to revise and understand the textbook. Maybe go back to all of the registers and understand a little bit about the textbook. If you have difficult time in that class, if you're very interested in hardware design, there's an elective class from Dr. Vemory. He's a really great UC professor. He's a very great UC professor. Sorry, I forgot this. So that class is called Intro to VLSI Design. Okay. In that class, you basically learn how to maybe, you know, not theoretical design, but now you design the actual circuit. And the cool thing is you will design the whole circuit in that class, and they have kind of like a chapter 2 class after that class that in the VLSI design you make a design for one class, and they will send that design into a manufacturer to make your chip for you. So that is very nice. After they make your chip for you, it will come back, and the next semester you will try to test that chip. So there will be another class to teach you how to do testing on your hardware. So this skill, but this class right here will be the foundation for it. So if anytime that during your academic career, if I'm still around, just like email me, let me know if you need any help. I'll try to help as much as I can, even you're not in this class anymore, or if you just need to talk to maybe some academic advice or something, I would love to talk. And if you see me around UC, just come up and say hi. I would love to talk to you. So I hope you have a good semester, and I'll look forward to give you the final exam. Last but not least, please give me the feedback for this class. This is the first time teaching for me, so there's a lot of things I need to improve. So if you really enjoy the class, you can give a very good feedback. I really appreciate it. If you did not enjoy the class, please do not go on Rate My Professor. You can tell your feedback honestly on your course evaluation. I will read that, and I will see how can I improve in the future. So thank you very much for just attending the class so far, and I hope you learned many things from the class. So I'll see you guys in the final. Bye bye.